Hey, thank you for looking at this video presentation. I'm Tongmeng, and I'll introduce our work PCC Proteus, where we design a congestion controller for internet transport. It is fundamentally motivated by our observation that most current designs on internet congestion control treat all traffic the same and simply aim at fair sharing among competing flows. However, with the surging amount of applications sharing the internet, congestion control without awareness application needs may not be enough. Here, we give some representative examples of internet applications. They all require network bandwidth resources to accomplish data transfer. However, users may have different timing requirements for different applications. When applications with elastic timing requirements compete with different primary applications with inelastic timing, more bandwidth can be allocated to inelastic ones. So overall, users of both types are happy with their experience. For example, for system update, even though it may induce a large volume data transfer, users may still be okay if it takes longer time, especially when that happens overnight when the user is sleeping. That said, an application with elastic timing may act like a bandwidth scavenger and back off against competing primary flows. Thus, our goal in this work is to design a congestion control scavenger. It should only go with any remaining bandwidth left by competing primary flows. And during the computation, the performance of primary traffic should be minimally impacted. To be specific, how shall we define such a scavenger? Let's look at an example. Alice and Bob are roomies, and they share the same wireless router. Now Bob needs to download a video presentation file from a shared Google Drive folder. Since this is the only data flow under the Wi-Fi network, it will be unreasonable to consume all available bandwidth. Then, sometime later, Alice opens her laptop and starts watching YouTube. With fair sharing congestion control, the streaming and downloading flow will equally share the bandwidth. But in our case, that causes frequent rebuffer during video streaming for Alice. Now, if Bob does not need the downloaded file in several hours, the downloading flow can actually back off and lets the streaming flow take most bandwidth. By doing so, Alice may enjoy both higher video quality and no rebuffer. So from the above process, we can extract the key design goals for a congestion control scavenger. First, when competing with primary flows, it should minimally impact their performance. Ideally, the primary flows should experience throughput and latency almost as if the scavenger were not present. Second, when there are only scavengers on the bottleneck, they should act like a traditional congestion controller, which requires them to attain fair and full utilization with low inflation. Furthermore, when Alice's local video buffer is almost full, the streaming flow can also switch to scavenger priority temporarily, so it gives some bandwidth back. That enables faster downloading without impacting video QoE. Thus, these different priorities are preferably implemented as a single protocol, so a flow can dynamically switch between them. With the definition in mind, a practical question would be, would such a scavenger be useful? We think different entities on the internet can have incentives of choosing to use it. Specifically, a user may run different applications at the same time, and enforcing the scavenger priority for those background applications can help improve the primary application's QoE. Similarly, a device manufacturer may want to minimize the impact to user experience when updating system and software in the background. And content providers may adjust the relative priorities among their different services, such as in our previous example with both YouTube and Drive from Google. They can benefit from increased overall experience for users around the world. From these examples, we can see that a scavenger may be needed if both of the two conditions are satisfied. First, there are applications and flows that are time insensitive, and the cost for them to be scavengers is negligible. Second, choosing to use a scavenger creates the opportunity of benefiting. Unfortunately, we don't have too many choices for a scavenger in existing literature. LabBet is the main existing protocol. It tries to control the inflation below 100 milliseconds. However, it has problems with respect to all three of our design goals. First, it allows the RTT to be inflated by up to 100 milliseconds. That may be too aggressive even as a scavenger, especially when competing with latency-aware protocols. And even when competing with aggressive primary protocols such as TCP/cubic, for example, we conduct dash experiments with different number of concurrent videos using the home Wi-Fi network. When there is a LabBet flow running in the background, the dash bit rate can be reduced by 35 to 75%. So the yielding goal is not fully fulfilled by a LabBet. Second, given its current implementation, it may observe an already inflated minimum RTT. That will cause unfair competition advantage. As shown by the throughput trends for 4 competing LabBet flows here, latecomer flows could unfairly dominate previous flows because they observe larger minimum RTT and thus are allowed to induce more inflation. This is a well-known issue for LabBet, which is called latecomer advantage. So similar to yielding, the performance goal is also not fully satisfied. At last, LabBet is implemented differently from most primary protocols, and thus, at the moment, it fails to satisfy the goal of flexibility. Therefore, we are strongly motivated to work on a robust and consistent scavenger for internet congestion control. In this work, we designed Proteus, which satisfies the 3 design goals for a scavenger. It employs a utility-based architecture based on PCC. Then, we design utility functions for primary and scavenger priorities and extend them to a hybrid mode. In addition, to deal with networks with high variance, we propose heuristics to handle non-congestion related noise. Let me give an overview of each design component. To start with, our architecture is inspired by the utility-based framework in PCC. The sender tries out different sending rates. Then, according to packet reception results, different performance metrics are calculated. Provided these performance metrics, the sender uses a utility function to calculate utility value corresponding to different sending rates. After that, a rate control algorithm determines how to change the sending rate so as to empirically maximize the achieved utility. For details on how that works, you can look at the past works on PCC. In this work, we extend this framework to a modular architecture. First, we introduce a utility control module. It has a library of utility functions. Each of them is constructed from carefully selected performance metrics. According to inputs such as application requirements and QoE in real time, the utility module can determine which utility function to use and switch on the fly. All those utility functions can rely on the same rate control algorithm, which we adopt from past PCC works for now as a rate control module. In addition, our noise handling heuristics operate on the received RTT samples and the calculated performance metrics. Next, let's continue to our utility functions. We designed 3 utility functions corresponding to primary, scavenger, and a hybrid priority, respectively. As I just explained in our architecture, each utility function utilizes selected performance metrics. So our first step is to identify a performance metric for scavenger. To gain some insights, we start by analyzing several penalty metrics used by existing primary protocols. First, packet loss is a traditional metric used by almost all TCP variants, as well as past PCC works. On the spectrum of buffer occupancy, packet loss is a pretty late signal because it only happens after the bottleneck buffer is full. Then, RTT gradient is a metric used by PCC Vivace for latency awareness. It is defined as an average rate of RTT change and can signal inflation when seeing an increasing trend in the received RTT samples. So it's much earlier than packet loss. Besides, some protocols may slow down if RTT exceeds a threshold. LabBet belongs to this category. Depending on the value of these thresholds with respect to bottleneck buffer, it could come even later than packet loss, or lie between loss and RTT gradient, or be similar to RTT gradient. With all these already used metrics, we want to find an earlier signal so the resulting scavenger yields quickly to those existing primary protocols. And our answer to that is RTT deviation. It is the standard deviation of successive RTT samples corresponding to a sending rate. RTT deviation captures the dynamics of the buffer level caused by flow computation and can signal such computation earlier, even when there is no consistent inflation. As shown here, when there is only a single flow on the bottleneck, buffer occupancy is relatively stable and low. Then, when a competing flow starts, it begins to probe for bandwidth, which can cause brief moments of increased buffer occupancy. This will show up as positive RTT deviation. And only after that, when the competing flows has ramped up and the bottleneck is approaching full utilization, will RTT consistently increase and then stay consistently high. In fact, we may never reach this later phase if the competing protocol is trying to keep the buffer low. So this is the intuition for why RTT deviation gives us an earlier signal of flow computation. To see if this intuition really works, we performed a simple experiment. We use a fixed rate UDP flow to observe the two metrics on an emulate bottleneck with abundant buffer. In the figures here, we compare their PDF when there is no other traffic with the case when there is Poisson arrival cubic flows. All cubic flows we initiated are short flows, and with a small flow arrival rate of 3 per second, our test reflects a low utilization case. Obviously, when there are cubic flows, RTT deviation shows a different PDF peak from the no computation case, while the distribution for RTT gradient is not as distinct. Therefore, we select RTT deviation as an important metric in our scavenger utility design. We base our utility function on the one in PCC Vivace. It rewards sending rate by a power T that's smaller than 1 and penalize RTT increments and packet losses. Due to limited time, you can find the details in the original paper. Then, our Proteus P utility function adopts the Vivace utility function, except that we ignore negative RTT gradients. By doing so, we intend to not reward the sender for going far below the capacity, and it is shown to improve flow convergence. Then, Proteus S utility function is the same as Proteus P, but adds a new term penalizing RTT deviation. Because RTT deviation is a signal not used by existing primary protocols, and it is an earlier metric in signaling flow computation, Proteus S is expected to consistently yield to many primary protocols. We also proved in our paper that a unique and fair equilibrium is guaranteed among homogeneous competing senders using Proteus P or Proteus S utility functions. That is crucial for our goal of performance. You can refer to our paper and the Vivace paper for all details on our utility design. The Proteus P and Proteus S utility functions can also be extended to a hybrid mode, Proteus H, where the sender starts in primary mode under small sending rate and switches to a scavenger mode when the sending rate is increased above a threshold. Here, we should clarify 2 key points. First, switching to a scavenger mode does not mean the sender will stop increasing the sending rate. Full utilization will still be guaranteed all the time. Second, when there exist competing flows, the sender switching to scavenger can benefit them by possibly more bandwidth share. Then, the application needs to set the switching threshold wisely, so Proteus H results in good QE for the application. As an example, we developed a dynamic thresholding strategy for ABR video. This strategy changes the threshold based on 3 conditions. By default, it would be enough if the switching threshold can deliver the maximum video bitrate smoothly. In our experiment, we set it to 1.5x the max bitrate. When the local video buffer is almost full, the threshold can be decreased, so competing flows may have more bandwidth share and better QoE. Whenever rebuffering happens, that is, there is no chunks left in the buffer, the application sets the threshold to infinity to guarantee the sender stays in primary mode until the video resumes. With such a dynamic threshold, Proteus H should enable more flexibility for network-wide utility. For noise handling, we try to filter out RTT samples that are likely from batch ACKs, which is common in wireless networks. Also, we determine whether to ignore the calculated RTT gradient and deviation based on the error in linear regression and the long-term trend for the two metrics. We don't have enough time to go into details, but you can find them in our paper. Next, for evaluation, we implement Proteus in user space based on UDT, using quick compatible function APIs. We also implement a video adaptation emulator to test our hybrid utility mode. Our experiments are conducted with emulated network and Wi-Fi connections to Amazon cloud servers. We compare two Scavenger protocols, Proteus S and LabBat, and let them compete with different primary protocols. To evaluate how well the Scavenger protocol yields to primary protocols, we let different primary protocols compete with LabBat and Proteus S respectively. Then we compare the throughput ratio of primary flow, which is calculated at the primary flow's throughput when running with the Scavenger flow, divided by its throughput when running alone. Ideally, the target value for this ratio is 1, meaning there is absolutely no impact from Scavenger to primary flows. In our experiments, we iterate through all combinations of emulate bottleneck setups in the range shown here. The figure shows the CDF of primary flow throughput ratio. In the median case, BBR achieves 7.8% higher throughput when competing with Proteus S than with LabBat. For cubic, such a gain is 28%. And for latency-aware Proteus P, the throughput gain is increased to 280%. The yielding performance of Proteus S is also robust on the live internet. Using different Wi-Fi connections to AWS cloud servers in different regions, we obtain the CDF of different primary protocol throughput ratio, competing with both Proteus S and LabBat. We found that all the primary protocols achieve higher throughput when competing with Proteus S than with LabBat. Then we evaluate the performance of Proteus S as a general congestion controller. For the case with a single flow, we don't have the time to show the figures, but Proteus S can achieve the same utilization with significantly smaller buffer size while inducing significantly less inflation than LabBat. And with multiple competing flows using the same protocol, we look at the Jane's fairness index. As shown here, the fairness index for both Proteus P and Proteus S stay above 90%, but LabBat may have decreasing fairness with more competing flows due to its latecomer advantage issue. Next, we show the network-wide benefits resulting from our hybrid mode utility function. Our experiment setup is illustrated like this. Using an adaptive bitrate video emulator, we stream one 4K video and 3 1080p videos at the same time on an emulate bottleneck. For each run, the videos are randomly selected from a corpus. Different bottleneck bandwidth are tested for each video selection. And we consider two cases where all video flows use Proteus P and all use Proteus H. We expect Proteus H to achieve better video QoE, especially for 4K video. Because under Proteus H, the 3 1080p videos switch to Scavenger at ascending rate smaller than that for 4K video, which enables 4K video to have more bandwidth than fair share. And that is validated by the achieved rebuffer ratios. These two figures present the average rebuffer ratio for 4K and 1080p videos under increasing bottleneck bandwidth, respectively. Under 70 Mbps bottleneck and when Proteus P is used, the ABR algorithm fails to deliver the highest 4K bitrate, which explains the smaller rebuffer ratio in that case. And with larger bottleneck capacity, Proteus H can lower the rebuffer ratio of both 4K and 1080p videos by up to 68% and 33% respectively. At last, to evaluate how our noise handling heuristics work in practice, we run single flow tests, again using different Wi-Fi connections to AWS servers. We present the CDF of normalized throughput for each protocol in this figure. First, Proteus S achieves very similar performance to LabBat, but slightly worse in this particular case. However, we think the goal of yielding is more important for Scavenger, and considering the significant yielding performance gain of Proteus over LabBet, we think Proteus S is still a better design choice. Moreover, it outperforms COPA and PCC Vivace, two main latency-sensitive primary protocols. So our noise handling heuristics are in fact effective. However, if compared with more aggressive protocols such as TCP/Cubic and BBR, Proteus S is inferior. So there is room for improvement in future work. To sum up, we focus on internet congestion control scavenger in this work. Based on the utility-based Proteus architecture, we design utility functions for different priorities. Specifically, we design Proteus S utility function for scavengers. It is based on RTT deviation and satisfies our goals of yielding, performance, and flexibility. Several future directions include improving noise handling and incorporation of Proteus into other platforms like Quick and Kernel. And thank you for listening. We welcome you to check out our codes on GitHub and email me for any questions.